Yeah, that is really saying. I'm very proud of you.
Do you sorry. Do you know how to display it as in presentation mode on your computer?
Oh, because it's sharing online. Like that?
Perfect, yeah.
Oh, it's because that's what's being
Yeah,
shared online.
yeah, perfect,
Okay.
yeah. And you're also not mute.
No, I'm not. No.
Perfect, yeah, then we can start now.
I don't think we're unmuted. Oh, 1 sec. I just got to do this because it's now. And then.
And do you want to be recorded while you talk?
My face?
Yeah, or not?
No, because I might walk that way.
Okay, perfect.
Yeah, this is fun. Now I don't know what's on the next slide.
We're about to start. So hi everyone, welcome to the public talk. It's my pleasure to welcome postdoctoral research fellow Dr. Lauren Rhodes here at McGill University, who will be giving the talk 50 years of gamma ray bursts, the most powerful explosions in the universe. And the talk will be giving a summary about the history of the theory and the experiments that led to the development and the knowledge that we now have about gamma, about these super energetic events that are taking place in our universe. Before we actually start with the actual talk, I just wanted to, those who have been here for a while, know that at TSI and at McGill Physics, we are committed to equity, diversity, and inclusion. So it's very important to us that everyone feels welcome. So if you have any concerns during the talk, please feel free to reach out to me or to any of our volunteers. And yeah, also if you have any suggestions or feedback concerning these public talks, feel free to reach out to this email. We are really happy to receive some feedback, and I hope some of you scan the QR code as we are collecting data and like about our audience. And it's also an opportunity to win a McGill Physics map, which is a nice item. So yeah, I think we are now ready to start our talk. And please join me in welcoming Dr. Lauren Rhodes.
Good evening, everyone, and thank you for trekking out in the snow. I know it's pretty rough out there. Yeah, today I'm going to talk to you about the history of the field that I do a lot of my research in. So I work on various types of transients. These are objects that kind of appear and then disappear from our observations. And in particular, I'm going to talk to you about the history of gamma ray burst, a particular type of transient that that I personally am very interested in. Now, in order to kind of start our story this evening, we have to go back to the Cold War. And actually, I was telling some of my friends who were sat down at the front here earlier that before I started really putting together this talk, the only things I knew about the Cold War were from X-Men. So I had to do quite a bit of reading before I realized that I would be like barely qualified to talk to you about the first slide this evening. So yeah, the Cold War kind of started up at the end of the Cold War, end of World War II happened, and it was a result of the Soviet Union implementing communist governments in all the Eastern European countries that they liberated from the Nazis at the end of World War II. And the US and the UK in part weren't too happy with this. They thought this was like a threat to their democracy. And over the coming nearly 20 years, there was a lot of, say, tension between the two groups of people. Now this but only got worse when the two, both populations started building nuclear weapons, and especially so when the Soviets started storing nuclear weapons in Cuba, which culminated in the Cuban Missile Crisis, and nearly had mutually assured destruction. But this was all kind of used, it was all fine, but only because of a year later when the nuclear test ban treaty was signed by both parties. Now, this ban essentially literally stopped. The idea was that neither country and anyone else either would be able to test nuclear weapons on the surface of the Earth. That was the idea. And as a way to enforce this treaty, the US, pretty quickly actually, only 2 weeks later, they launched their first of many, a series of satellites called the Vela satellites. Now, a given set of Vela satellites was two objects. So here's a pair here. Each many-sided shape object, I'm not going to guess how many shapes, is a separate satellite. And in each launch, there would be two of these, and they would go on either side of the Earth. Now, this is one of many terrible schematics I love to put in my slides. And so the idea being that each pair of satellites could see the entire surface of the Earth at any one time. So in order to do that, they were orbiting the Earth at a distance of around 125,000 kilometers above the surface of the Earth. So that's about a third of the way between us and the moon. And so they would orbit around like this, just where I'm going. But what was really interesting about this was because they were so far away from the Earth's surface, they had no issues about the Van Allen belt or any radiation from the Earth's surface. They were also able to see everything else that was going on away from the Earth as well. And so over the many years that the Vela satellite program was running, fortunately, no nuclear tests were detected. But what was detected, among many things, were 16 bursts that they didn't know where they came from. So the first being something that came out of the US military, took a really long time to declassify these objects. So the first was detected in about 1967, and it took until 1973 that the public was made aware that these bursts from space had been detected. Now, if just for comparison, if we were detecting nuclear tests on the surface of the Earth, the flashes of gamma rays that would have been seen, that would have been detected by the gamma ray and the X-ray detectors on board the Vela satellites, those flashes would have lasted maybe a millisecond or even a millionth of a second. They are very, very, very short flashes. By comparison, the bursts that were detected that weren't coming from the Earth's surface lasted between seconds and 30 seconds. So what I've got here on the right-hand side is the only plot in this publication. They were really short and sweet back then. I really appreciate that in their papers. So we have three different panels. And on the y-axis, we have how bright each object was. So you'll see there's the flat line. That's just when they were detecting nothing. Then it shot up and it was a bit wobbly, and then it came down again, it flattened out again. And each one of these is three different bursts detected by three different Vela satellites. And this is 3 of the 16 bursts that were detected in total. So there we go. We have on my lovely timeline here, we have the first, that was the birth of our field. So that was in 1973. Okay, I'm aware we're now 52 years later, but I'd like 50 sounds better. And at the end of the day, I'm an astrophysicist. So like 52 and 50 are exactly the same in my head. And you probably could also equate that to 10. And yeah, so this field was born. We knew that these things existed, and it was super exciting. But all we knew that there were flashes of gamma rays being detected in space. We knew nothing else. We didn't know what was producing them. We didn't know where they were or anything like that. So that became the problem. So over the coming 20 years, or many, many years, we're still doing this now, subsequent satellites and missions were launched into space with the aim of detecting more of these. And it was because we didn't want to just detect on the order of 10. We wanted to be detecting hundreds or thousands of these events so we could understand their statistical properties. So what I've got here is from the BATC gamma ray burst monitor. And it's basically a map of the sky. In the same way that we have flattened out maps of the Earth, this is the same for the sky. And each dot on there is a different gamma ray burst. And as you can see, there's no real preference in a direction. They're pretty isotropically distributed, pretty spread out evenly across the sky. And that was really cool. So now we knew kind of they could be produced coming from any direction. We knew they definitely weren't coming from the sun. But this meant that they could be from really, really nearby or really, really far away. So that was causing an issue. But what we could at least begin to do is understand something about their statistics. So in comes Krista, oh, sorry, super French. Sorry, Vela to you too. I can't pronounce her surname. I feel really bad. So Krista, her first name, was the first person to have a PhD thesis on gamma ray bursts, and this was in 1993. She has recently taken semi-retirement. She's been doing amazing things for the high energy astrophysics field since then. And she's just a really cool, awesome woman as well. But what she published was the first kind of beginning to look at these events as a population. So what we have here is we took a sample, like say 100 bursts, and we looked at how their durations, how long they lasted, were distributed. And this distribution we see here is what we call bimodal, and that's because it has two peaks, right? So if you look down here, just below 1 second, there's a bump. There's like a larger number around like just less than a second. Then when we go above a couple of seconds, we have this other bump. And the idea was at the time that this meant that more than one type of object could be producing these flashes of gamma rays, these gamma ray bursts. But still, we didn't know quite what it was, where they were. We just knew there could be multiple channels producing these systems. And yes, this was great. This was like a massive thing because this meant that people could begin to come up with some theories. And it meant that it wasn't just going to be one theory that was the correct answer. And then that map I showed you had many, many different dots on. And that was because we were detecting about 300 gamma ray bursts a year. And that led to many, many thousands of theoretical papers, ranging from things that could be quite reasonable, gamma ray bursts from neutron. These are all genuine papers. I've not made any of these titles up. From neutron star formation, strange stars. I still don't know if they're even real. Various ideas, relativistic dust grains. So this is like dust like you see in the air or even smaller, moving at nearly the speed of light. I don't know how that would be possible, but who knows? And then we have goblins. Someone really went a bit wild with this one, but we have many, many ideas. And yeah, but one of the problems still was that as you will hear me say that a lot in this talk, was we still didn't have enough information. It was still always, we need more and more information about these things. So in 1995, on the 75th anniversary of the Great Debate that was held in order to discuss whether what we call nebulae in the sky were actually in our own galaxy or were other galaxies themselves, part of the American astronomical community came together for a second great debate. And this was the Great Gamma Ray Burst Debate. It was held at the Smithsonian Museum in Washington, D.C. And it was held between Donald Lamb and Bohdan Paczynski. And so Donald Lamb believed that these gamma ray bursts were happening really, really nearby to us. He thought they were happening all in our own galaxy, but was able to explain the fact that they were evenly distributed across the sky and not centrally localized like many objects in our galaxy are. He was able to explain this by gamma ray bursts were produced when neutron stars were produced in supernovae. So when stars exploded and they produced neutron stars, these neutron stars were kicked out of their position where they were first formed and had high velocity such they could be all over the sky. And these were producing these gamma ray bursts. But Bohdan Paczynski took a very different view. He didn't say, we think it's this. He was like, we know that there is, if we take how bright these objects are, there's a point at which we can't detect the faintest objects anymore. There's a flux limit. And he took this to mean that there was a point at which we were no longer able to see these things because they were just too far away. And the way he presented this understanding to his community was that this meant that they have to be extragalactic. When you were taking their distribution and their brightness properties, they couldn't be within the Milky Way themselves. And so I was at a conference last year, actually, and the organizer of this conference was speaking, and he read us out all the emails in his after dinner speech, or all the letters at the after dinner speech about how they organized this conference. And I never thought I would be so interested in listening to people just like going backwards and forwards organizing a conference. But it's such an important piece of history to our field that it was very, very interesting. But the debate was settled 2 years later in 1997. At the top left-hand side of the slide here, I've written GRB, so gamma ray burst, 970508. Okay, so this gamma ray burst was detected on the 8th of May, 1997. Okay, that's the naming convention we use in our community. In some communities, objects are named after their coordinates, but ours are named after the date they were detected. And if, say, you had many detected on the same day, you would start with A, B, C, D, da, 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 da. I think the highest I've noticed in my career thus far has it been 5 in one day, so we've gone up to E. But the great debate was settled when in a kind of nice kind of culmination of ways. So many of those theory papers that I was showing you before, they predicted that after the flash of gamma rays, there would be a multi-wavelength, slowly evolving transient called an afterglow. Yeah. And so people were looking for these, and they had found one earlier in this year, I think. But they were really hard to find because the satellites that were detecting the gamma rays, they wouldn't kind of tell you, oh, it's in this galaxy. It would say it's over there, which is not useful when there are many, many galaxies over there. So it became a real race to try and find the first afterglow, really try and localize these events. And this is what we see here, okay? So on the left-hand side, we have the telescope image, and the little thing labeled OT stands for optical transient. And so they were able to confirm they saw an afterglow. This is what we call a light curve. It's how the brightness of an object in different colors, that's literally the different color points, evolves with time. We saw it decay in this like nice line, but we weren't able to just use this information to say, okay, these events have this electromagnetic afterglow thing. We're also able to work out how far away it was by looking at how the brightness of this object changed with the wavelength of light or color. So this is the original plot from the paper. And what we've labeled here in the different, it just looks like a wiggly line, essentially. This is not what I'm an expert in. To me, this just looks like a wiggly line. But there's some labels on the plot that correspond to different elements that were produced, what are thought to be produced in the explosion. And they compare these to the models, and they see that they're offset from where they should be. And they use this to work out how far away that object is. And it was telling us that these gamma ray bursts were in fact extragalactic. The Bowden-Paczynski was correct in his debate that these are cosmological events. And we've now observed many of these events, and we know it to be true. I think the current record for a gamma ray burst, the most distant gamma ray burst that we know of, was produced when the universe was 1/11th of the age it is now. So these are incredibly luminous events that we're able to see across the visible universe, which is very cool. So we now know that there are more than maybe one type of progenitor system for these events. We know where they come from. We know they can't be in our own galaxy. And it was the combination of detecting high energy photons from huge distances was telling us that these must be incredibly energetic events. You have to have something incredibly energetic that is producing these gamma rays that we're able to see. And so now we can go back to those theories and see where these objects were coming from and what could be going on in order to produce them. So there's two parts to this story, because as I said earlier on, we had our bimodal distribution. We had the two peaks that we thought could come from two different populations of events. And the first one of these came just a year after we realized that these things were extragalactic. So in the late 90s, basically all gamma ray burst physics was done. All the theory, all the observations, I could just stop there, really. But then it wouldn't be a very good story, and I wouldn't be stood here talking to you about my research today. So this is an image of a nice galaxy, a nice pretty galaxy, and there's a little arrow pointing towards a very, very bright blob. And now this very, very bright blob was originally thought to be a supernova. So it was just a regularly evolving, it was a massive star that evolved and exploded. But what was different about this supernova was it was exploding too fast, okay? Which sounds like a bit of an odd phrase to say. But this was like an odd supernova. It wasn't what everyone was beginning to understand was happening in these systems. And I have I love data, I love light curves. That's basically all I spend my time looking at. And believe me when I say that this isn't what one of these light curves should look like. It should be more flat at the top, or the color should be slightly different. But what they discovered pretty quickly was that, when you don't know what's going to be on your next slide, you're like, oh, have I said the right sentence? So what they concluded was that this star was exploding too quickly, and it meant that they were able to infer that the star that has existed beforehand was what we now call a Wolf-Rayet star. So this is a massive star that during its lifetime has really, really strong stellar winds. So it ejects material across the whole of its lifetime, which creates this beautiful, like, fluffy thing around the outside. And when they're rapidly rotating, these objects, which is why a lot of this wind is ejected from the system. And they were able to, how do I say this? They were able to see where the gamma ray burst on the sky had happened. And then they saw this rare, interesting supernova. And they were like, these two must match, because this was a supernova unlike what they had seen previously. But we'd seen many other types of supernova previously, and we hadn't seen gamma ray bursts come from those. So this was a particularly interesting type of event that we had now discovered. So this was like part of the job done. And for many people, this is still interesting. So sometimes we observe these types of supernovae and we don't see the gamma ray burst. And so this is still very much an open field of research, is why do sometimes we see it and sometimes we don't. The second half, we had to wait a whole, go back a slide. The second half of this story, we had to wait basically 20 years. There was a humongous gap. We knew where half of the GRB population was coming from, and the other half, we had no idea. We had we had ideas, but we had no concrete proof. And so this was finally solved on the 17th of August, 2017. About a year before I started my PhD, and this event is why I was then able to do my PhD. And it's thanks to these detectors that exist in the US and in Italy called gravitational wave detectors. And they don't detect light like a telescope does. They detect that when space-time itself moves a little bit as a result of colliding black holes or neutron stars, basically. So what we see here is that exact thing going on. So on the bottom panel here, this is what happens if you take two merging neutron stars. So these are Montreal-sized balls of neutrons, of atomic matter, and you collide them in space. And this is what really annoyingly, I had a video of what it sounded like, and I couldn't get it to put it out. And so this is frequency, and we turn it into a sound, and you hear this little like chirp mass, like this little chirp noise. It sounds like a bird almost. And so these gravitational wave detectors, they detected these merging neutron stars for the first time, and amazingly, 1.8 seconds later, one of these X-ray and gamma ray detectors in space detected a short gamma ray burst, which is what we're seeing in the top three panels here. And there immediately it was confirmed that short gamma ray bursts were coming from binary neutron star mergers. But that isn't the end of this part of the story. Actually, this one event filled in was like the perfect event in, if you're interested in binary neutron star mergers. Everything happened in one event, and we've all been really disappointed about the whole field since. So not only did we get the confirmation that these synthesized balls of neutrons colliding in space were able to produce these flashes of gamma rays, we were able to see what was happening afterwards. So I said earlier about this afterglow, and that's what we see here. Again, we have a beautiful image of a galaxy, and then we have these 3 panels where over the course of several nights, we see this object get fainter. And like I showed before, we had the brightness versus time plot. That's essentially what we're seeing here. But what we could also do was, again, see how brightness changed with the color of the light. And what we were able to do is we were seeing elements in that spectrum, we call it, that were not had not been observed before in a stellar explosion or in an explosion in space. And so I love these plots. It's the periodic table. And every square, every element has yellow on it. It's produced in these explosions, okay? So for like the longest time, so many of the elements that were produced in space, we just didn't know where they were coming from. And in one like week of observations, we had this answer. So this was a really, truly groundbreaking event for our field. So the conclusion for the other half of these events was they could be produced in these binary colliding neutron star mergers. But before I go on, I've tried to be very careful on how I word this because it's very hard to go from saying gamma ray bursts, because as a community, we call gamma ray bursts for the whole thing. And it becomes very confusing when you try and communicate this with other people. But what I've said is that we've had 2 different types of objects that can produce these flashes of gamma rays. But I've just said, okay, that's what was there. And then we saw a flash of gamma rays. But because the 2 different types of events are very, very different. Okay, but you'll notice both of them. So I said that the star was rapidly rotating. And when we had these merging neutron stars, they're going around them like this and they collide. So we knew that there had to be some process that was similar in both that could produce this flash of gamma rays, that it was only when you were looking at a statistical level, when you were looking at a large number of these events, that you were able to see that there were differences in them. So we knew that they were hugely energetic. They're able to produce high energy photons. You need a lot of energy to do that. We knew they were really far away. Oh yeah, okay, now I remembered I made this slide. So the problem there's so much energy involved in these. So I haven't given you guys any numbers, right, for how energetic they are. So our rough understanding is that these things contain 10 to the 55 erg of energy, which, unless you're an astrophysicist, means absolutely nothing. It's also 10 to the 48 joules, if you can think in light bulbs. Or at one point, I did actually work out how many asteroids that killed the dinosaurs that you would need in order to get the same amount of energy, but it was still like a billion of those. So it's not very useful. These numbers aren't very useful. But I'm not a fan of putting equations in slides, but I actually think here this is very useful. So if we wanted to really understand how much energy is in these systems, we can use Einstein's equation, E equals mc squared. Okay, we would need to have 5 times the mass of the sun to convert immediately into energy to produce these explosions that we were seeing. And that was if everything was perfect. Okay, unfortunately, the universe is not that way. In reality, we need more like 500 solar masses of material to be immediately converted into energy to create these. And we don't find 500 solar mass stars. They don't really exist. So this is a really big problem for us. But there was a way around it. So the idea being that instead of the gamma ray bursts themselves coming from this very, very spherical energetic explosion, so coming from the supernova itself, or from the place where we saw all the new elements being created in those binary neutron star mergers, what if we had some different geometry involved? What if, as well as our spherical explosion, we had some collimated, we call it a jet, some collimated outflow that's pointing towards us? Now, this could work. So this came about as there was a model called the fireball model, which despite it's being called a fireball model, it's not a ball, it's a jet, it's a column of material that is ejected close to the speed of light in these systems. But the interesting thing is that these jets, this material that's ejected at the speed of light is pointing right at us. So when we look at it, we can't tell that it's not a sphere. We just see it as something that's moving very close towards us. We just assumed it was a sphere, because why wouldn't it be? So in order to test this, it's very hard to do, because how do you know that something's moving at this? How do you infer that something is moving at the speed of light? How do you test this model? Jumping back a little bit to 2003. I didn't write the gamma ray burst in. Okay. So on the 29th of March 2003, if you really care, there was a gamma ray burst that was really, really nearby. And it was so nearby that we were able to do this really cool experiment you can't usually ever do. Or you can try, but it's usually not very successful. If you have, and you can do it with a radio telescope. So I said before, you had this afterglow, this multi-wavelength, slow evolving transient that happened after the gamma ray burst. Now, what some astronomers in the US did was they wanted to observe this radio object. And what they did is they took all these radio telescopes that exist in the US. They have some in New Mexico, I think there's one in Hawaii, and there's some further north. My American geography is really bad. And what's cool about radio telescopes is you can combine them all together and treat them like one massive telescope, one that's the size of the continental, or the size of the Earth. And it means that when you have such a massive telescope like that, you can see things that are really, really, really tiny. And so what actually they were able to do was they were able to watch this gamma ray burst expand as it grew. And as it moved towards us, the thing appeared to look bigger. Because it's when if you move your hand towards your face, it gets bigger as it moves closer to you. And when they were doing this, they were like, that's moving really, that's growing really, really quickly. And so they turned each one of those data points, those sizes with a function of time into velocity, into speed, okay? And so here I've made this plot. So instead of having size as a function of time, we take each data point and we see how much faster than the speed of light would the object have to expand to be that big. And I don't know I know like most people on the front row are my colleagues, so they definitely did physics. But Einstein famously said that nothing can go faster than the speed of light. But all these data points are going faster than the speed of light. So that's a little bit of a problem. But this is a really cool effect called apparent superluminal motion. And it is an effect that happens when we see something moving very, very close to the speed of light. Now, I'm not going to go through the maths because that would be really cruel. But my grads in my lecture next Thursday do have to go through the maths with me because they love me so much. But this was the clincher, right? We had this irrefutable test that something was moving close to the speed of light. We had our confirmation that this fireball model was correct. And that's awesome. That's kind of almost the end of our story, actually. I have no idea how much time I've got left. And yeah, that's kind of, I could say, cool, done. Before I even started my PhD, gamma ray burst physics was done. It was finished. But what's amazing now is I get to work on these objects, given the history we have, and find all the problems in all these theories, which I love doing. Because these people were geniuses, and I get to be like, haha, I can see how you guys are wrong. And yeah, so here's my final horrible schematic. So this was kind of the general idea. We have our big stellar explosion, our binary neutron star merger, and somehow inside it, and I say somehow because we don't know, the answer is honestly, we don't know. These jets, these collimated outflows are launched close to the speed of light and pointed towards Earth. And yeah, so this is a really, really nice picture that we have going on here. And what's really cool is the way that we study these objects means we can differentiate the different sections of what's going on. Some people are super interested in the supernova or in the outflow, in the explosion in the binary neutron star merger. But me, myself, I'm interested in the jets themselves. I'm interested in how particles are accelerated in these. How can you have something that is moving that close to the speed of light, yet has mass? How are there particles in there? Because you would think that would mean it would have to move a lot slower. I'm interested in the energy budget. I'm interested in the shape of these jets. Do they just look like this, or do they have some more structure to them? And that's kind of, I guess, in theory, what I thought I would be doing as a PhD student in the 2020s. And in ways that's happened and in ways that hasn't. So I have two quick examples. So the first is GRB 221009A. So this happened on the 9th of October, 2022, which I distinctly remember, very sadly, was a Sunday evening. This happened on, and I was sat on the sofa in my home back in Oxford, and my friend called me. They were like, "Lauren, there's this object that's gone bang. You need to put the telescope on the object now." And I was like, "What, dude? It's a Sunday. Please don't." But it turns out I didn't really have a life, so I did it anyway. And this object we now refer to as the boat. Okay, so this is the brightest of all time. It's like the Simone Biles of gamma ray burst physics, or Tom Brady, or that Wayne Gretzky, the ice hockey player. I hear he's very good. And yes, this is a cool picture that explains what's going on here. So we have count rate. So instead of photon detection rate, like the number of photons we detected, in gamma rays and X-rays, we call them counts. We call each photon a count. And on the left-hand side here, we have all the other the previous record holders for this. We've detected some pretty bright ones over time, but this one was over 10 times brighter than any before. And in fact, it was so bright that we detected it across the solar system. So I didn't know this, but every single NASA or ESA probe that's sent out into the solar system has high energy particle detectors on it. And this one was detected by Voyager 1, which turns out nearly 6 times further away from the Earth. 6 times further away from the sun than Neptune is. It's really, really far away. It took a whole day for this light to reach us after it was detected by Voyager. That's how far away it was. But we're able to actually see in all the detectors on all the NASA probes how this burst traveled through the Milky Way, through the solar system, which I think is really cool. And then the second one, because I don't have time to explain that other slide, which is sad. It's GRB 230307A, which is you guys can mark it out at this point. Which really, really broke physics for most GRB people. So at the beginning, I showed you guys this plot, and I said we had our long gamma ray bursts and our short gamma ray bursts. Well, this was a long gamma ray burst. It's there. It's the line that you see. And so we went and studied it, and we were like, oh, because it was pretty bright. We were told that the brightest of all time event was a 1 in 10,000 year event. And then 6 months later, we got the second brightest of all time event. We were like, oh, that doesn't seem right. I still haven't found anyone that can explain it for me though. So this was JWST, Jet First Space Telescope, had recently launched. And so we asked for time with the James Webb Space Telescope. This is part of a program I was on. And up there in the top left-hand corner was the object. And here, all the way over here, is its host galaxy. Okay. Now, this is really far apart. Okay. We actually didn't think these two were associated for the longest time. We assumed that we couldn't actually really see the host galaxy. It was just really faint. It was really, really far away. That made kind of more sense to us initially. And turns out what we were seeing here was actually a binary neutron star merger that was masquerading as a long gamma ray burst. So now, for the last 50, well, just under like 30 years, we've had this really, really nice scenario where we knew that short gamma ray bursts were produced by colliding neutron stars and long gamma ray bursts were produced in exploding stars. And then this object came along and kind of like ruined everything. So what's great to know is that I still have a job for the foreseeable future, because these things keep happening every time. This is one of the great things about developing new instruments, or other people developing new instruments, which then I use. Is that every time they just develop something that's more sensitive, we find more problems in the theories, and we get to create new problems for ourselves to solve. And yeah, so hopefully there's a lot more GRB physics to come in the future. And on that note, I'd like to say thank you. And if anyone has any questions.
Thanks a lot. We have a lot of time for questions. So if you don't mind, maybe repeating the questions.
Yeah.
So that our online audience can hear us. Yeah.
If no one has any questions, I've just stunned you all to silence with my amazing talk. Mark?
So is the boat the brightest because it's intrinsically the brightest, or is it bright when it's close to Earth?
So the question was, is the boat the brightest because it's intrinsically the brightest, or it's just close to Earth? Yeah. So it is incredibly nearby. It's so nearby that we could do that experiment where we were able to see the thing expanding with the big radio telescope. But it is also intrinsically fairly energetic as well. It produced the highest energy photons we've ever detected. Some of these particles are so energetic, it's like more so than what like CERN is producing in terms of like energetics. It's like, yeah, you don't want to be hit by one of those particles, one of those photons. It would hurt. Yeah. Zach?
How did we figure out that the event of 2023 was actually connected to its host galaxy?
So this was something called what's the coincidence? Probability of chance coincidence. That's what we did. So they could place, given the observations, they could place a limit on what we, given what regular long gamma ray burst host galaxies look like, we could place a limit on what we expect to detect. So we could say, okay, we didn't detect anything. This is what it should look like. So that's how far away approximately we think the host galaxy is, and how luminous and energetic would that make that gamma ray burst. And so that would make it far more energetic than any event ever that we've ever detected, not just in terms of how bright it was, but actually its intrinsic energetics. And then this was close enough by in like not projected on the sky, but actual real distance, that in terms of the stellar evolutionary pathway that would take to create two neutron stars that could then collide and produce this event, it was possible that they could leave their galaxy and travel far enough in that time frame between them forming and merging that they could be that far away. Yeah, and then they were able to say, okay, what is the chance of it being close? Yeah, but there was like a lot of additional physics involved in that. Yeah, there was a pizza bet placed on it. And yeah, so one of my old boss owed a good friend of mine pizza out of it. I think he did pretty well. So, yeah. Jesse.
So gamma ray bursts tearing down the barrel, the jet.
Yeah.
Is there any possibility of seeing the jet in other wavelengths when it's not down the barrel?
That is a fantastic question. So the question was, are there any chances of seeing the jet when it's at any other angle? So this is a huge field of research. So us trying to search for events such as these supernovae that are produced in these gamma ray bursts, these ones that are expanding faster than we expect them to. What people do is they point their, say, radio telescopes, because we don't expect radio emission necessarily from the supernova itself. So they point the radio telescope at those and they wait, basically. And they say, okay, so over some period of time, the jet can't continue to move at the speed of light. It has to decelerate after some time. And so as it decelerates, the effects of special relativity mean that we can finally begin to see the jet as it decelerates, and the light begins to be visible to us. And so then we hope to see it later on. But so far, in the public domain, so that in the literature that's published, there are no cases of this. But people are constantly trying. So yeah, I have a friend at Cornell who works on this. And the reason I said not in the public domain is because we're going to a conference together in 2 months, and her title of her talk is like potential. off-axis jet. So I really hope she finds one, because for us, this solves a lot of problems, because we've been looking for a really long time and we haven't seen anything. And so then it's like, okay, why don't we see them? Yeah, does that help? Yeah. Someone over here had a question. Hi, sir.
I can understand what you explode current traveling this light comes through the
Sorry, could you repeat that? I don't think I quite heard you. Sorry.
disposed of the appear to
How does that happen? Like, how does it appear like that? So the question is, yeah, how does it appear that it is moving at the speed of light? I don't want to do maths. Okay, let's see. How do I explain this?
like, is it a plasma that basically is continuing to emit
Yeah.
as it approaches the
Yeah, so it's not a so a blob of material is ejected from the system and continues to move towards us and expand over, it can be many years. And so as it's moving way, like very, very close to the speed of light. And because of the sideways expansion of it, and because it's happening close to the speed of light, the effects of special relativity come into play, and that's how it kind of appears to be moving faster than the speed of light, but actually isn't. I can recommend a textbook if you really want to know. Yeah, sorry, it's very hard to describe in a narrative sense. Yeah, sorry, I can't give you a better answer than that. Yeah.
About the last source you mentioned, GRB 230309. So you mentioned that it was a kilonova.
Yes.
So to my knowledge, there is only one current gravitational wave detection of a kilonova.
Yeah.
Or a neutron star.
Yeah, the GW17. Yeah.
So how do we know, or how are we able to distinguish and say that this was also a kilonova?
So the observation, so the question was, how were we able to know that this was a kilonova? Because there was no gravitational wave event to tell us that it was a binary neutron star merger. What's really cool is that JWST has many instruments on it. So this is called near cam, so it's just a camera. But not only were we able to just make an image of the field, we were able to make a spectrum, so to see like how the light is different brightnesses and different colors. And so when we took the spectrum of it, we saw a lot of very heavy elements, and actually a lot of heavy elements that weren't seen in the other event, but were predicted to have been there. So there's a couple of papers on it that various people claim they see, like tellurium, I think was one of them that they saw, and that was a particularly heavy element. They were like, oh, we don't know how else this could be produced. And yeah, and you can also do things like you can see how hot the emission is, and that sort of thing, and that will tell you what exactly it was. Yeah. Does that help?
Yeah.
Cool. Hi, sir. Yeah.
distribution plot, with all the spots on it.
Yeah.
If these are jets,
Mm-hmm.
those spots are a jet,
Yeah.
and that's in one.
Yes.
dimension.
Yeah. Yeah. This is, yeah, it's exactly. Yeah. It's, yeah. I mean, so if we detect, say 300 a year, and the solid angle of them is, I mean, it's of the order of, okay, I'm just ruining the homework for my students. It's on the order of 0.00001 per galaxy per year. The reason we don't detect a lot of these, the off-axis ones, is because by the time that they have like slowed down enough such that we could see them like enter into our viewing angle, they're too faint for us to detect with telescopes. So we have many surveys with many instruments like optical and radio and X-ray that are just kind of over the course of, say, a year, or in the radio, or maybe even every day in an optical telescope, they will scan the whole sky looking for events like this. They are looking for these objects that aren't pointed directly towards us. And there are a couple of cases where they say, okay, maybe this is one of these events, but it's very, very hard to say conclusively, because it might be the case that your gamma ray burst detector wasn't looking that way at the same time. Yeah, but these are a lot of events, but also the universe is very big and they're incredibly luminous, so it's not entirely surprising that we detect this many. Yeah, does that answer your question? You don't look hugely convinced by my answer.
The numbers.
Yeah. Mm-hmm.
But it just struck me that it's a pin of light.
Yeah.
Okay. It's a pin of light.
Mm-hmm.
And we've got that over 30 years or whatever.
Mm-hmm.
2000 over 30 years.
Yeah.
Strikes me that you could do some analysis and expand that into a 360-degree thing, a circle. And much of it's that.
Yeah. And they totally are. We just can't see them because, yeah. Yeah. No, there are loads. Yeah. And there are many people who work on working out the exact number, because part of the working out the exact number of how many there should be is working out how wide that pin of light is. So if it's, say, like, I don't know, if it's very, very, very narrow, I mean, we're only going to see a very, very small fraction, but the wider the angle, the more we're likely to see. And so there are actually a lower number intrinsically. Yeah?
We have a question about,
Oh, okay.
so were there failed gamma ray bursts observed? So lack of gamma ray bursts despite the evidence of supernova, neutron star mergers, matching lighting conditions for gamma rays.
Yeah, so there are events that could be deemed failed gamma ray bursts. So they have various names in their own right. So some of these are called like orphan afterglows or dirty fireballs. And there could be cases where, so I said this was the best explosion is the exploding star scenario, because these are the most common. And when the jet tries to get through the star that's exploding, it might not get through. We don't know why that's, it might not, but it could be that sometimes it doesn't have enough energy, it's not moving fast enough, and it just can't like pierce through the star. So this would be a failed gamma ray burst, but what would happen in this scenario is that energy that was in that jet gets dumped into the star. So you might not get enough energy to produce the gamma ray burst, but you still might see evidence of something that is kind of moving pretty quickly or very, very quickly. And yeah, this could be, instead of gamma rays that we see, we could see X-rays instead. So there is a field that's become very popular in the last few years called fast X-ray transients. And this is like, we don't quite know what exactly we're looking for, but we find lots of very interesting looking things. That this could be one of them, these failed gamma ray bursts. Yeah. Hello, sir.
Have you seen any drawing up?
This is also not confidently is my answer. There are people who say there are many people in the world that work on this. So the really cool thing about, say, looking for a gamma ray burst and a fast radio burst is that the telescopes we use a lot of the time to detect these fast radio bursts, you don't have to like physically steer the dish. You're just kind of looking at the whole sky all the time. So you could be on source, like the gamma ray burst can happen, and you can be on source, say, immediately. So you could be waiting and be like, okay, if there's a fast radio burst, we should be seeing it. And we're trying really hard to find them. There's been a few candidates, but I don't think anyone says with certainty at this point that we found one. But if we did, that would be very, very cool. And I'd be very, very excited if we were able to detect that. Yeah. Thomas?
Really nearby, really bright gamma ray bursts be dangerous to anybody on Earth.
Yes. It absolutely would, yeah. So one of the things I didn't say about the boat, I got so excited because I wanted to show the Voyager plot. So this thing was so bright, and it didn't happen like that nearby. That's the concerning part. It still happened in like many, many galaxies away. When it hit the Earth's atmosphere, it actually caused the atmosphere to like heat up a little bit. So the whole atmosphere went like whoop, for like a couple of seconds. And so the whole gamma ray burst community was like emailing each other, being like, "Oh my God, did you see this gamma ray burst? We should get our telescope on it." But when we then got information from the like radio communications sector, and they contacted like the community, and they were like, "Hey, what just happened? We stopped being able to communicate with radio waves for a few seconds." And it's because of how the atmosphere like changed, it meant it was less transmissible to radio waves. And so this was an object that was at cosmological distance. It was many billions of light years away. If, say, one of these was in Andromeda or in the local group of galaxies, yes, this would absolutely be dangerous. I think it's a theory for one of the mass extinctions was maybe like the gamma ray burst, like hit Earth. But the good thing is, it's not good, but okay. The good thing is because these things travel at the speed of light, you wouldn't know it's coming. So it would just kind of happen, and it's fine. Everyone's yeah. But yeah. Yeah.
I love the Voyager plot. It gives me so many ideas.
Uh-huh.
If you have all these satellites around the solar system and they can measure times when gamma ray bursts in it, can they use it to localize the source? And also, can they say anything about the solar systems like electron content or something like that?
So we do this already to an extent. So there's I think called the International Planetary Network, the IPN, and it's controlled by a guy out of Louisiana State University. And they do this I think it's like one of the Mars missions and then various things around Earth they use to localize. I don't think the signal to noise of the detections we get are such that we can talk about the like electron content in the solar system. That is a really cool idea. I like that a lot. Yeah, if we were able to put more dedicated facilities on these missions, then maybe that would be very, very possible. Yeah, but it's a cool like commensal way of doing science. I thought I saw another hand. Naya.
You mentioned that like we still don't fully understand what is powering these gamma ray bursts. What's the wackiest or most fun theory that you've come across?
So it just sounds so unfun. So the idea. So the question was, we don't understand what's powering these events, like actually what is launching the jet. Yeah, I'm gonna stop at that because I don't have a better way to work. Yeah. So there are two theories as to what is could launch these events. They're both named after the people that came up with the idea. So there's Blanford, Siniak, and Blanford and Payne. And so Blanford just really smashed jet launching mechanisms. And there are people who say we can tell the difference between these two scenarios based on the observations that we can collect. I am not convinced at the current time. I just think it's too much. There's too much uncertainty in our understanding still. But yeah, there's just magnetic fields involved, and anything involving magnetic fields just is too complicated and scary, and yeah. But no. But cool. Yeah, hi.
So, I'm a model here. I just saw a little video to understand a little bit the subject, 5 minutes for kids. And the gamma ray you're talking about is like a firework that you can see from any spot, or is that literally has to be pointing at us? And the theory is that you can see other ones in other directions, but it has not been proven yet.
So the question was, is the jet? Yeah, is it like a firework? Is it spherical, or is it a jet pointing only at us? And yeah, so it's the latter. So there will be ones pointing elsewhere in the universe that people like aliens elsewhere in the universe can see that we can't see, and vice versa. And yeah, so I mean, it's not that it's like infinitely narrow and it's pointing like only at us. So it has like some width to it, and so sometimes we get this was what this cool video shows. Actually, it shows that it's not pointing directly at us. So this was a movie made by an X-ray telescope. So in the middle, that's the brightest point of the gamma ray burst pointing directly at us. And what happens is, because the jet isn't infinitely narrow pointing at us, it's pointing elsewhere in the Milky Way, and the X-ray light is bouncing off electrons that exist in the Milky Way and then like bouncing into our line of sight. And because it's like doing this all around us, it creates these rings. And so as the light gets like brighter and fainter, the light reflected off of the electrons get brighter and fainter as well, and creates this really, really beautiful, these really beautiful videos. Initially, I didn't know entirely how this was useful, but I was talking to a colleague, and they said that this mapping of the electrons in the Milky Way was used to show that the Milky Way at like large distances away from the center is actually way puffier than we thought it was. So these observations were able to tell us like more about the structure of the Milky Way than we otherwise knew, which I thought was pretty cool. And then we just get nice movies as well. They have a really good color scheme. Like obviously X-rays aren't purple, but like I thought this was pretty cool. Now I'm gonna stop that before everyone is like mildly hypnotized by it. Cool. Yeah, Jesse?
So the three types of gamma ray bursts, right?
Mm-hmm.
Like the long ones, the short ones. So one supernova, massive star supernova,
Yeah.
binary neutron star.
Mm-hmm.
And then you mentioned that you've got like typical host galaxies. I'm just curious.
Yeah.
If you have like good statistics on the separation between the two types of gamma ray bursts and their types of host galaxies, like people live in star forming galaxies and supernova, and is that like totally true, or do you just not know that?
So the question is, are there typical, can we say like with some amount of confidence that there are typical host galaxies that host short gamma ray bursts and long gamma ray bursts? So within reason, this is usually the case. So we expect long gamma ray bursts, which are produced by massive stars, to live in star-forming galaxies, because the way that stars go through their like main sequence life, it's the so the more massive the star, the faster it dies. Okay, it gets through its fuel really, really quickly, and so it gets through it so fast that we can't have expected star formation to have stopped in the time that we see the long gamma ray burst happen. So we expect long gamma ray bursts to happen in very, very star-forming galaxies, and then short gamma ray bursts, these binary neutron star mergers, take a very, very long time to get to the point of merger. Okay, so you've had to go through two fairly massive stars reaching the end of their lives and producing neutron stars. And that happens quite quickly, but the problem is they're going to happen at some distance from each other, and then you have to get these two to go from orbiting on this distance to colliding, and the way that they fall into each other, like in a spiral, is via the emission of gravitational waves. So it's like going down the plug hole, like, yeah. And that can take billions of years. There are ways to speed it up. There are more ideas of how to speed it up. But so that takes so long that we expect over the time scale that's happened, the star formation would have ceased. Obviously, there are exceptions to every rule. So as also, I guess, kind of is the case with this one. I mean, okay, I don't know that much about galaxies, but there looks like there's a lot of stars in there. Like, I don't know, this looks like there's a lot of ongoing star formation in this system. So this, like, I mean, this whole system is an exception to the rule, but you can say that. And then often, sometimes we get like actual stellar explosion, long gamma ray bursts that happen way outside their host galaxies. And we're like, how did that happen? Like, how did that star form out there? That actually doesn't make sense. So when the supernova, we think what happened is when the two supernovae that produced the two neutron stars happened, each one of those supernovae, it wasn't a fully spherical explosion. So it like kicked the system a little bit, one, and then the other one happened and it kicked it a bit more. And so it ended up out there, which is pretty cool. But yeah, but like we love having the exceptions to rule, because that's like the ones that we find interesting, and that's the ones where it really tells us where our models are, like we can really break apart the models and see what's wrong with them. And yeah, but also there's not going to be one single model that it will explain every observation we ever have. We try, but it doesn't work. Yeah.
So we received another question regarding the interaction between gamma ray bursts and high energy neutrino events.
Okay.
So person was wondering whether there are any correlations with observation of these two types of
So there has been no confident association, like I don't even think I can say confident. There has been no association of a neutrino, specifically a neutrino, and a gamma ray burst event. I'm sure there are many models that say there could be, but it's very, very hard to detect neutrinos. We have the closest we've got is detecting very, very high energy photons, like way, way higher than gamma rays. But at the moment, we haven't detected a neutrino, unless they know something I don't. Yeah. Cool. I think I've tired everyone out.
There are no more questions. We
Oh.
would like to thank Lauren for this beautiful talk. So first of all, I would like to announce the next public talk, which is actually going to be a panel. So in light of UNESCO proclaiming 2025 the International Year of Quantum Science and Technology, we're going to organize a quantum science panel. Even if you're in astrophysics, that could be a really nice opportunity to get to learn more about this. The panel is going to feature Bill Koish, who is a theorist here at McGill, and Claude Crepeau, who is an expert in quantum cryptography at PTS. These two experts will come together and talk more about how quantum science developed since its birth in the early 90s, beginning of the 20th century. You will hear more about this through the emails and on our social media. As a last thing, I would like, if your name is Charlie Shannon, you won the raffle to get a McGill physics mug. So feel free to take the one who's on the table. And again, thanks so much for joining us. If you have any feedback, anything, reach out to me. It was a pleasure to have you. Thanks. And let's thank Lauren again.